over here where we started out trying to apply this equation that we have been deriving since based on the material that we covered yesterday, and then we derived this particular form. So we are trying to apply this equation to track particles in an idealized respiratory domain now, unlike what we did yesterday when we were not assuming anything specific in terms of the anatomical realism of the geometry. So now we are trying to apply this to figure out the particle transport trajectory. And just as a recap, this is the geometry that we assumed probably is a good estimate of the upper respiratory tract. This is circular and then straightens out. Eventually, when we solve the numerical example, we'll see that we can adopt realistic cross-sectional areas, lengths in this geometry, and then figure out the answers for it. Cylindrical polar coordinates. This is what we figured out for the fluid velocity and the particle velocity. We are assuming that the packet of fluid is moving like this, so the radial component was assumed to be 0, so it's just v fluid theta unit vector, and then for the particle velocity, it does have both theta and r component. Now, coming back to that equation, we are just plugging in the result fluid velocity and the result particle velocity. And as we figured out that there would be some terms that are time derivative of the unit vectors. So these are the terms that I said are correct, and I think there was a confusion if they are correct or not, just for folks to know where to access this. So I have uploaded this document under. So if you go to the cloud folder that was shared with you guys, there is a folder, subfolder called Channel Papers. There, look up this coordinates document. If you go to that document, so this has other details about different coordinate transformations. But I think if you go to the very last page, this is where I show dr dt and d theta dt. So dr dt is theta hat, theta dot, and d theta dt is minus r hat theta dot, which is what, if I go back now to the document, is what I had used. So the obvious next step would be to plug these things back into the previous equation. So let's do that, and then we are trying to isolate the theta component from the left hand side and the right hand side, and the r components as well, and see as we equate those components what we can get from there. So folks who just joined, we were trying to clarify whether these equations are correct, which we figured out is correct, and the corresponding document is under the Channel Papers folder on your cloud folder. Okay, so let's plug this into this equation, and again I am doing it here live, so if you find anything wrong, just let me know. Okay, so therefore putting the time derivatives of the unit vectors in the previous equation, we get, so the previous equation was this. So let me just copy the part. So tau dv theta dt times theta hat plus v theta d theta hat dt. So d theta hat dt is minus r hat theta dot plus dvr dt r hat plus vr dr dt is theta hat theta dot. And then on the right hand side, v fluid minus v theta theta hat minus vr r hat. Okay, now let's write it in the dt format. So dv theta dt theta hat minus v theta d theta dt r hat plus dvr dt r hat plus vr d theta dt theta hat. Okay, and this is equal to v fluid minus v theta theta hat minus vr r hat. Therefore, now we are ready to equate the components. So equating the respective components. So let's first equate the theta component. So we have on the left hand side tau dv theta dt, and then the very last term, so vr d theta dt is equal to v fluid minus v theta, and then the radial component on the left hand side is tau dvr dt minus v theta d theta dt is equal to minus vr. Okay, so let's call this as equation C. So today our equation B was this equation that we are actually using. So let's call this equation as C, which is basically the same equation, but now we have them with the cylindrical polar components equated, and as a result two separate equations. So let's see what we can do with these two equations now. But to solve these equations, we have to think about the initial conditions at this stage, which is what we started to discuss, or someone was asking if we need the initial conditions. But let's now actively think about what initial conditions could be reasonably assumed to solve the system. So initially, at t is equal to 0, so at t is equal to 0, what is going on? So in terms of what we are working with here is this basic system, right? The v fluid vector is the v fluid theta, and then we have v theta and vr for the particle velocity. So that being the case, let's brainstorm a little bit. So for the particle velocity, we have v theta as the theta component and vr as the radial component. Anyone guess what the v theta could be at t is equal to 0? Or what could be reasonably be assumed for v theta at t is equal to 0? Huh? Yeah, tell me v theta first, and then you can think about vr. V fluid, someone I probably heard v fluid. Yes. So as you embed the particle, you can assume as a reasonable estimate that the particle is first moving with the fluid. It doesn't have any R component as such. So we can assume that V theta is almost equal to V fluid initially. So that's an assumption. It probably is not precisely correct, but it's a reasonable mathematical assumption. The other thing that could help us is related to the geometry. So for example, if I look at this particular diagram, we can also write also the S, which is an evolving parameter over here, is R times theta. Do you guys agree? So S is R theta, but if we are rather tracking just the central part, we can also write this as S is equal to L naught theta, because that's how we are determining S, right? We are not determining S from any random point. So it is from the center of this inlet. So S is always going to be L naught theta. Okay? Now, if that is the case, if we do take time derivative of this equation, this second equation, S is equal to L naught theta, what happens then? So, if we take ds dt, L naught is constant, so d theta dt. So d theta dt, we are going to find whatever value we get for d theta dt from here useful in those equations, fine. But what is ds dt? Can we assume something for it? ds is, can we say that ds dt is v fluid? That is how the fluid is moving, right? We are talking of this as a packet of fluid moving with the S being basically the centroidal section, centroidal point. So can we write something like this, that this is hence V fluid L naught d theta dt.
This we are saying that just at the instant.
At any instant, not at the instant, but here for that matter we are talking about t is equal to 0.
F equal to the particle at the center.
Right.
Then
So basically think about the particle following this particular geometry. We are placing the particle at the center and what it's doing right after that. But at that very point, at t is equal to 0, we are assuming that it has the velocity of the fluid without any radial component. It is just turning up. It has a fluid in the direction.
the moment we do the ds value, means the information will be used for the entire part.
The ds dt information is for the fluid, not for the particle. That's how the propagation of S, as assumed in this diagram, is based on what the fluid packet is moving. It has nothing to do with the particle. Right? The particle can deviate from that S. That is the trajectory that, if you think of it in that way, it is the trajectory which a fluid particle which was at that point is moving. It's like a straight line.
Yes, we want to write the fluid density from some other particle.
Yeah. Because d theta dt is related to the particle's revolution in space. And we are using that, we are getting to this point by using the geometry that we appreciate.
And this fluid velocity will affect the trajectory of the particle by this d theta by dt. V fluid is equal to L naught d theta by dt. D theta by dt will go into that those equations.
Yeah. So basically what we are getting from here, so this can be plugged back into any of these equations. So that's what I'm going to do next. Okay, so let's, what, as he suggests, we are actually going to supplant this d theta dt into the previous equation. So let's write that down. So d theta dt is v fluid over L naught. Let's now go back to the second equation over here. We could have used the first equation, and you can do that what I'm trying to get at is show you a result that was derived rather recently in literature, and the fact that we can derive that based on the mathematics that we have been developing for the last 2 years. So let's use the radial component and see what we get from there. So we have from the second equation of the second sub equation of equation C, from the second sub equation of equation C, we have tau dvr dt minus d theta dt is v fluid over L naught, that we have found out. But there is one v theta. So what is v theta here? We have assumed that at t is equal to 0, v theta should be the v fluid. So we put that here. So as a result, this becomes v fluid square, right? So we are putting both v theta and d theta theta from these two equations that we have derived. On the right hand side, we have minus VR. Okay? Let's now try to take the dVr dt on one side and put the rest on the other side. So we have dVr dt is minus VR plus V fluid square by L naught divided by tau. The next thing would be to integrate this. I'll take it slow because I'm bad at integration, so I'll do it by substitution, not to miss anything from here. So let's assume that this term, the numerator, I'm going to assume it to be something. So let's assume that this negative VR plus V fluid square over L naught is some term beta.
So tau will follow VR by tau. Minus VR tau plus.
Oh right, VR over tau. Yeah, you're right. Yes. So let me just scratch this part for now. It would be too crowded. So what we should have is, from this second sub equation, dVr dt is negative VR over tau plus V fluid square over L naught. Right, correct, right? Yeah.
So do you have assumed v theta at t is equal to 0?
V theta? Yeah.
V theta equal to v fluid at t is equal to 0.
Yeah.
But we are integrating it over the entire line.
Yeah.
So how can we justify this assumption?
So V theta is a function of time, right? So it can change over time. But what we are assuming is that at t is equal to 0, that V theta value was V fluid. Now, in terms of, okay, now I get your question. So, is your question something like, is the V theta going to stay constant throughout?
Yes, throughout the.
Right. So, my argument is yes. So, if you think about a particle moving, if it is following the exact streamlines, something with a very low Stokes number, for example, it's always going to have that V theta, which is the V fluid, which is staying constant in this case, and it is moving with the streamline. But if a particle has inertia, there would be a radial component, right? Like if it has a strong enough mass, it moves away from the streamlines. And that would be done with the VR, which is something that is additional to that V theta effect. And as a result, V velocity is different, of course. But that V theta part is dictated by the fluid motion. That's what the argument is.
V theta also I think can change.
V theta,
Yeah, when we talk about inertia.
Depends on what you mean as the change. So you are saying that if the particle is,
Because I think it can be so bad.
yeah,
So it can be the beta of the time.
If the tau is very big, so the Stokes number would be like very high.
yeah, if the Stokes number is very high, then beta will change. But with the Stokes number being very high, the point is whether the particle will have enough time for the beta to change before it goes on the wall because of the VR. Especially because we now have this circular tract, right? With the Stokes number being high, that means that the particle also has high inertia. So there is other countering effect which was not there yesterday. We did not have that kind of thing.
Maybe we can integrate this from tau to some time because at t is equal to tau, the Vt does
Yeah, yeah. That could be done as well. And this is an open topic in the sense that the paper that I'm trying to derive the result that we are trying to derive was just published a few months back. And the assumptions that are going into this work could be improved, right? And that itself leads to the possibility of new work that is publishable at a good enough journal right now. So let's move on from this. So this is correct. So let's call this equation D. And from here, yeah, this is what I was trying to get at. dVr dt is minus Vr plus tau V fluid square by L naught over tau. Right? So now it is correct. So I have that balancing term over there. So let me replace this numerator with some single term. So minus Vr plus tau V fluid square by tau is, sorry, by L0 is some term beta. So dVr dt is minus d beta dt. So therefore in D we have minus d beta dt is equal to beta over tau, right?
Plus B.
Yeah, so this dVr dt is, so I'm using this equation. dVr dt is d beta dt, negative, and then that entire numerator is beta divided by tau. Am I missing something?
On the right hand side, it should be just beta.
Over here?
No, it is correct. It is correct.
So basically I'm using this equation. Okay, so let's now change the sides and do some integration. So d beta over beta integral minus 1 over tau dt. So integrating this becomes natural log of beta minus t over tau plus some constant. So to evaluate this constant, let's think about what is happening at t is equal to 0. So at t is equal to 0, beta we have already assumed to be this numerator that we had replaced, right? So this numerator over here. So at t is equal to 0, it is minus Vr plus tau V fluid square over L naught. At t is equal to 0, we said that the particle does not have any radial component to its velocity. So this is 0 at t is equal to 0. So we are just left with tau V fluid square by L naught. So if we plug this back in over here, so at t is equal to 0, therefore ln of tau v fluid square by L naught is equal to t is equal to 0. So the first term on the right hand side is 0 plus this constant. So the constant is e to the power of tau v fluid square by L naught. So let's move this over here. So we have natural log of beta is minus t over tau. Actually, this last step is wrong. We can just use this constant to be the natural log of this entire term. So let's put this directly over here. So minus t over tau plus log of tau v fluid square divided by L naught. Okay. So now let's get the logs on one side. So ln beta divided by this term tau v fluid square by L naught is minus t over tau. So beta divided by v tau v fluid squared by L naught is e to the power of minus t by tau. So let's go to the other page. Now let's put what we had about beta back over here. So beta is minus Vr plus tau V fluid square divided by L naught is equal to tau V fluid square by L naught e to the power of minus t over tau. Or Vr is 1 minus, so tau V fluid square by L naught 1 minus e to the power of minus t over tau. So this is the time function for Vr, the radial component. Now going back to the geometry over here, what are we trying to study here? We are trying to study whether we can form an analytical framework that can predict particle deposition. Those particles could be pathogenic aerosols, those particles could be pharmaceutical particulates. The theta component as such is useful but not as useful as the R component, in the sense that if a particle is over here based on the same theta, had it been over here, it is going to get deposited, right? And the main distinction between this point and this point is controlled by what is the R. So if you make sure that the R component is big enough, it will be landing on the walls even if theta is small. So the theta value, the range of theta value would not necessarily tell us anything. Because for the same theta value it can be deposited, it might not be deposited. But the R is a certain criterion that can tell us whether the particle has deposited or not. And that is the reason why we are trying to drive this analysis towards the R component. And now, with that logic, we do have how Vr is varying over time. So now we are very close to a solution which can develop a generic criterion for wall deposition. We just have to do one more layer of integration. So we have the Vr. So therefore, to predict the wall deposition criterion, we have to integrate again. So dr dt is this right hand side on equation E. So tau v fluid squared over L naught 1 minus E minus T over tau. Right? So let's now do some more integrals. So we have, let's assume that minus T over tau is U. Therefore dt is minus tau du. So we are going to use this one. So therefore integral of E minus T over tau dt is minus tau e to the power of u du, or minus tau e to the power of u, with u being minus t over tau. So let's use this directly over here. So we have dr tau v fluid square over L naught integral dt minus integral e to the power of minus t over tau dt. And this becomes r as a function of t, tau v fluid square over L naught t, and then this term, so plus tau e to the power of minus t over tau, right, plus some constant c. Let me know if you see something that's wrong. Okay, now again we need to evaluate this constant of integration. So the initial condition over here is at t is equal to 0, we have to figure out some initial condition that can be used here. So like before we were trying to find the initial conditions that relate to the velocities. Now we have to think about the initial conditions that relate to the spatial position. So what is the initial position, or what is r at t is equal to 0? Second? Yes, so we had assumed the distance from the center to be L naught, so at t is equal to 0, it is L naught, correct. So at t is equal to 0, we have r as L naught. That being the case, let's put things back here in the equation that we just derived. So L naught is equal to, this term is 0 because t is equal to 0, this term is 1. So we basically have tau square v fluid square divided by L naught plus c, and hence c is L naught minus tau square v fluid square by L naught. Right? Okay, let's now put this back in this equation and try to simplify this a little bit. So therefore RT is tau v fluid square over L naught t plus tau e to the power of minus t over tau plus this c, which is L naught minus tau square v fluid square by L naught. Okay, so this is interesting because where we are heading at is, if you think about the geometry that we started out from, L naught is the central location, and then this particle is deviating from that central string line, right? And that extra term that we are getting, so there is this L naught here, but the remaining terms can be clubbed together, of course, and those remaining terms can help us determine whether the particle is going to this upper wall or lower wall. So it is very interesting how it can be done. So let's do that. Let's simplify this a little bit. the L01 intact. So we have RT is L0. Let's take this tau v fluid square common. So tau v fluid square over L0 T plus this tau is common, so tau times e to the power of minus t over tau and minus 1 for this one. Let's call this equation F, I believe. So now the rest of the analysis could be driven using this term, which signifies the deviation from the central streamline. Okay, so let me write down what the couple of things that I just said into words before we use that particular term. So for example, as this RT becomes L0 plus L. So what is capital L? It's the radius that we had assumed. So if it exceeds that value, then that means that there is upper wall deposition. So the particle will deposit on the upper wall of the idealized respiratory geometry. Right? But that is not all. It can also deposit on the lower wall. So L0 minus L is also a valid criterion. So let me write that down as well. So similarly, for lower wall deposition, this RT would be less than L0 minus L. You can think of this as greater than equal to and less than equal to as well. That's just some triviality. It doesn't matter whether you say equal sign or not. Basically, you are crossing that threshold, either the upper threshold or the lower threshold. So let's use this and try to set up the criterion. So therefore, for upper wall deposition, so we are using this E form. So L naught plus tau V fluid square divided by L naught T plus tau e to the power of minus t over tau minus 1 is greater than L naught plus L. So the condition comes out as tau V fluid square over L naught T plus tau e to the power of minus t over tau minus 1 is greater than L. So here L is the mean radius of the respiratory tract. But so L is the mean radius of the respiratory tract. So this equation, does it look familiar to any of you? We just read this equation from the last time. So I was working on this lecture material in December during the Christmas break. My wife and daughter they were traveling to my in-laws place, so that gave me a lot of downtime to work. So I derived this equation and I could have gone in a different direction as well. I could have used the other components, but I first thought that the radial component is interesting, so let me derive this. So derive this equation, it sounded kind of nice, like the way the derivation was done is kind of brilliant. And then I knew of a paper which I have been dying to read for a while, especially because it's coming from a collaborator, Sunny Dan, who is on some of my clients. So I started to read the literature and then I saw that he has already derived this. And he published this just a few months back, 6, 7 months back. So that's why I made you guys at least take a look at that paper. So I'm going to put the paper on the screen now. So this was the paper, simplified models of aerosol collision and deposition for disease transmission. Since all of you did read the paper, anyone wants to just summarize in 3 4 lines what it was about? Not the details of the scientific equations and whatnot, but what he did. Anyone?
In this basically two models are described. One is the aerosol deposition and another is there is a difference in how a particular deposition happens with respect to the aerosol respiratory disease.
Yeah. Okay. He looked at two different time scales. First of all, and time scales. So first, how is the room level mixing happening? Right? So that is what the paper starts out with. And then he goes to what is happening, what is going to happen inside the respiratory tract.
Per hour, how much is the recirculation is happening?
Yeah.
What is the radius of that infected person?
Yeah, so that's the root level modeling. Like what kind of transmission an infected host might be carrying out with the others. And then once, let's imagine that I am infected, so I am giving out pathogens, and now Dr. Shamanto is getting infected, is getting exposed, and he is inhaling all these pathogens, and what is the generic trend of the particle transport inside the air? So that's where he went into next. But because I knew the overall story, that this is what he was trying to do, and what I don't believe that he claimed that he did all this work because he had like 2 layover days at a conference, so he had nothing else to do. So apparently he did all the calculations and that I don't believe that. But anyways, but this was a very elegant piece of work and I have been meaning to read that. But since I was developing material for this lecture, I thought that okay, the story is gradually getting to what Sun is in that paper. So after I stopped my calculation over there, I started to read this paper. I think I noted down the equation here. So this is equation 13. So I'm going to skip the details of the paper, of course, and I would encourage that you guys eventually go through the details because things like this could be done without any kind of hardcore computational support, without any experiments. You just need to plan 2 empty days around a conference and you can get this paper done. But let's go to this equation over here. So this was the room level modeling that he did. And then he's going to the aerosol deposition inside the respiratory tract. And eventually he's coming up with this particular equation over here, equation 13. So equation 13, let me make this small. don't know if it is visible or not, but let's try with this. So we have, I think I already missed equation 30 here. So yes, this equation. So what he had was alpha u integral over L naught. Now the word alpha threw me off because the symbol alpha threw me off because we don't really use alpha for time. So if you read the paper, you go back a couple of pages, alpha was the particular section in this case. T plus alpha is tau, t to the power of minus t over tau, minus 1. So here it is, based on the very basic level mathematics that we started out from yesterday. Essentially Newton's equation, right? From yesterday. And here you can derive something that can still be published, even in theoretical fluid mechanics, which is not trivial. Like so many people, as our common acquaintance once told us, that Navier-Stokes was developed 200 years back. What we are doing still now, but still there are things to do even if you have 2 days of layover. Okay. Anyway, so and then he used this to do some more, and the paper basically ends right over here. So not much else to study, but the great thing is we now know what are the different assumptions that went into this derivation, and you can expand on those assumptions, maybe make it more nuanced, and that itself could be a new equivalent study. But let's try to use this and see what it tells us about particle transport trends in the respiratory area. And for that, we have to do some numerical solutions. By the way, how many of you does have access to MATLAB in this room? Maybe through your laptop? Anyone? Not anyone? Okay. So then I have saved the codes on the share folder. I'll try to run them live over here in front of you. So feel free to use them later on. Okay, so just as a note, so compare this to equation 13 of Jung Scientific Reports 2023. Okay, now for what we are trying to do next is use this equation to figure out what the generic trend of the particles could be in terms of the spatial trajectories based on two very widely defined sizes. So I think in the work here, I'm going to show two particles, one with diameter 0.1 micron, one with diameter 100 micron, and see what happens. And check this particular criterion for that. So so based on the particle sizes, let's first figure out the particle relaxation time, that cofactor that is outside the bracket, and then we can take a look at the MATLAB code that I wrote.
So from here we can conclude that if the time is greater than the particle relaxation time, then the particle will definitely deposit on this upper wall of the.
Yeah. And actually, like once I run the code, you will see that the time it would take for the particle. So basically, the time it would take for the particle to reach the wall is widely different for the smaller particle with respect to the bigger particle, and which is expected. Based on the length of the longer time scale, it would be quite obvious where it is going to land. And based on the length of the shorter time scale, it would be also quite obvious where it's going to land.
So in this, like, wave fluid is the ambient fluid for the particle, right?
Can you repeat the
So
question?
like wave fluid is the fluid velocity.
Yes.
And the particle is not there.
Yes.
So does that mean that the particle hasn't disturbed the flow at all?
It is so. This is not a coupled system. The particle is not disturbing the flow. The flow is, so think about the way the equations have been derived since yesterday. The drag force is coming on the flow plane. The flow is impacting the particles, but the particles are not. And that assumption will be true even for the safety simulations that hopefully we are going to run tomorrow or after tomorrow. So it's a decoupled system in that sense. Now, your question could be, is that a good assumption? That's a valid question. Now, the thing is, if you look up papers in this field, their argument is, if you think about the volume of airspace and the flux that goes through it and the net volume of these particles, it is not necessary that there is going to be a momentum exchange between the particles and the fluid. So while you can develop it as a two-phase system in your numerics, but the eventual benefits out of that is so slim that it doesn't make sense to make it that complicated. But that is a foolish argument in certain sense. So I do plan to go into that territory and run it as a two-phase system. But then again, two-phase, like for example, I have other projects where we do have to consider the multiple phases. Like if you think about movement in very thin tumor vessels in blood channels, there the RBCs are big enough because RBC is what? Around 8 micron, white blood cells are around 16 micron, and those channels could be around 30-40 micron wide. So there you have to think about RBCs and WBCs as different phases. But over here we are talking about, you saw the dimensions, right? So even when you go to the alveolar channels, you have 500 micron. And the particles that we are talking about are 10-20 microns. So do we really need the multiphase assumption? Probably not. So, but the other thing is, not many fluid mechanicians like us have been active in this field. So if you go to any medical school, people might not be sure about what might entail either. So maybe because we are in this field and these things are evolving, we should try out all our tools. Okay, so as I said, we are going to use two diameter examples over here. So let's go to the next page. So take two examples. Of D is equal to 0.1 micron and 100 micron. So the V fluid, which is the inhaled airflow, by the way, Sunny also used a different symbol for the V fluid, so it was U in his formulation. So now I'm trying to set up the problem statement that we're going to solve. So V fluid, let's assume it to be 5 meters per second. Typically, this value is between 0.1 to 15 meters per second. The rho p, let's assume that we are still dealing with water particulates, so rho p is 1000 kg per cubic meter. We have this is the formulation that we are dealing with, so tau is there, and tau does have the slip correction factor based on the particle size. Now one may argue that do we need the slip correction? We don't need the slip correction probably for the 100 micron size. We do need it for the 1 micron. And that I think Devananda is the reason why the small particles have higher tract. So we can discuss this later on. It is because of the slip factor. But anyway, so we do need the CC correction. So let's put it there. So CC is 1 plus 2.52 lambda mean free path divided by D. So this is 1 plus 2.52 0.067 by 0.1 in the first particle and 1 plus 2.52 0.067 by 100 in the second particle. can you give me these two numbers? And let's stop here because after this I'm going to run that code and try to explain the code, so that will take a while. So let's calculate this C's and then we can pick up the rest of it on. How much is the first one?
2.6.
2.69.
6.68.
2.69. Let's take it as 2.7. So this is 2.7 for D is equal to zero point 0.1 micron. How much is the next one?
1.001.
Let's take 1. So this is D is equal to 100 micrometer. So that's why I said that you need it for the small particle, maybe not for the bigger one. So we are going to use the CC to calculate the tau, but let's pick up from here.
Can you become 10 minutes?